Thank you for inviting me. So today I will talk to you and try to bring things together about our vision of having such robots in our lives, where you need these robots to physically interact and be situated and embedded into our environments, into our world. And I will try to get you through some of the work that we are doing in my group that started with the funding of the Emi group that led to the creation of the team called iRosa. This is why you see this logo there. It means intelligent robotic systems for assistance, but eventually now we evolve into interactive robot perception and learning. And I will talk to you about how structuring our learning can allow us to bring this robot one step closer to the real world. So our vision and my vision as a roboticist and many robotics and AI researchers is to create these general-purpose robotic assistants that we have seen in cartoons and Hollywood movies that are these human-like robots that are able to manipulate and move around the environment. They can perceive the objects and the humans around them. They can learn multiple tasks, combine them and sequence them, and they can also adapt to human needs. However, we don't have such robots yet. The best interactions that we can have in our home environments are something like this, right? So where are the robots right now? So the robots right now, they are in industrial manufacturing, where everything is pre-programmed and very well structured, in warehouse autonomous navigation, in autonomous vacuums, but if you own one, you might know that you have to basically make space and fix your house before the robot starts, because otherwise it will get stuck. And finally, we have some autonomous driving, but even 10 or 15 years later, from Elon Musk telling us, oh, you're going to have autonomous cars and so on, we are not still there. There's a lot of things that we need to solve to enable robots to come into the real world. And then if we talk about service robotics, robotics that can be cobots, collaborative robots, service robots, robots that they can take care of the elderly, then there is a lot of complexity when it comes to manipulation, when you want the robot to interact with the environment and change the world. So manipulation is very difficult. Here you see an example of the Herb the robot from CMU. This is like 10, 15 years ago. They tried to train, then teach this robot to cut Oreo cookies open. And this is the policy that the robot learned. And this is an example of whole body manipulation with a humanoid robot. Also, MT showed before an example of failures with Atlas the robot. So things can work well when you program them very, very well and you keep a very structured environment. However, the real world is heavily unstructured and uncertain. So we need to combine some things in order to make these things work. And this is what I will talk about later. So in 1988, Moravec, a professor of robotics at the CMU, have stated that it is comparatively easy to make computers exhibit human-level performance when it comes to, for example, playing chess or the game of Go later on in 2013-15. But it is difficult or even impossible to make them acquire skills of a one-year-old when it comes to perception and mobility. And one of the bitter lessons, I think, that we found out in robotics and robot learning eventually is that you cannot try to solve the problem only considering that you need learning or only considering that you need classical approaches. You need to find the silver lining there. So I believe that viewing robots as disconnected systems from the geometric and semantic world and its structure is what makes any method, both classical and, let's say, modern, deep learning-based, fail, and then we cannot have methods that are capable of generalizing and scaling for real-world applications. So the question here is, how can we enable robots to reason and act in the physical world? And I will try to show you how, by structuring robot learning, we can achieve some of our desiderata. By robot learning, in case that you don't know what this field is the field that combines machine learning methods, supervised reinforcement, or unsupervised learning methods with classical robotics to allow robots to acquire skills through imitation and interaction with the environment. Now, the gist of our approach is that we need to take into account the structure of the problem to enable faster, safer, and more scalable learning of robot behaviors. And some of the desiderata of structured robot learning is to acquire coordinated and generalized manipulation skills, especially when we have these complex robotic systems with arms, head, torso, a base that can move around in the environment. We want scalable, long horizon behaviors, so a robot that can understand how to solve a task that requires many subtasks to be solved. And finally, we need fluid and safe human-robot interaction. So I will show you several key areas where we have been working with structured robot learning in terms of representations, exploiting scene geometry, exploiting classical priors, and even how we can exploit the geometry of the environment to form constraints in order to enable better learning that can transfer into the real world. So a disclaimer here, I will keep my talk high level, so you will not see much math. I actually removed them from my talk. So I will mainly focus on cool robot videos that do not, show robots that do not fail. So starting from representations, in order to connect perception with action, we need to create these representations that would allow us, for example, a robot to see a scene, like, let me start it again, like these videos here of some demonstrations of humans, and without needing expensive labels and annotators to see what is happening in the environment, to be able to transfer such actions into the robot. So we have recently proposed a method that takes some ideas from classical approaches in computer vision, so an unsupervised based approach that creates labels based on the entropy of the image. So we represent basically the pixels as being random variables in the image that it represents a lattice. We extract the entropy, how much information an image contains, and then we can basically create representations that we call key points in order to enforce them to contain the information in videos, so in streams of these images. For example, here, how does this then work on a very high level? We feed an image frame into a neural network, and then we enforce some key points that are the centers of some masks to actually cover the space of information. What you see highlighted is basically the entropy, the information of the current image frame. And now we can also exploit ideas from information theory. For example, we can take the entropy images of two consequent frames and the conditional entropy that represents how much information has changed between two frames, and try to reconstruct basically what is the expected change in the information in the new frame, and try to find a mutual information between what I would expect to reconstruct in the future, how much basically this key point represents about the image in a new frame and the previous frame. And by exploiting the entropy, we can create loss functions that allow us to create these key point-based representations that we call maximum information key points. And here is an example of our approach that, together with some regularizers that also allow us to turn on and off key points when we contain the information in the video, we can track both static and dynamic objects versus baseline methods. And we can also apply on top graph-based neural networks in order to learn how the scene evolves. And eventually, we can apply this in realistic videos like this one and see how when the hand will go out of the frame, the representation will basically only represent the object in the scene and will turn off the key points that represent the human hand and so on. And eventually, what we want is to actually transfer something like this and use it to do imitation learning. And for now, for the purposes of this work, we used a toy benchmark for imitation learning, and we basically surpassed the state-of-the-art performance by keeping this structured representation. So using, again, these graph-based approaches, we can keep the structure and learn different tasks. And we hope to bring it to the real world soon. But once we have a scene structure, there are a lot of things that we can do in order to enable robots to reason also over long horizons. So let's take an example here that it is an assembly task. So imagine that we have three-dimensional Tetris blocks, and they give you some sort of volume, and they tell you, OK, find a way to combine all these Tetris blocks to fill up a volume, without knowing exactly the end locations of these blocks. This is a combinatorial optimization problem because you need to find basically this sequencing, and you need to ensure in the meantime that you want to have stability, and therefore classical approaches of like search most likely fail. So we started initially trying to understand what is the best possible way of optimizing this problem to find basically the optimal sequence if we here draw some facades of area that we want to fulfill. But then we figured out that when we put the robot in the loop, things become even more difficult because not all sequences are actually realizable and feasible by a robot. So we considered to take into advantage the scene representation. So we basically represented the objects in the scene and the robot with some graph. And we let reinforcement learning methods, so methods that they learn by trial and error, to try to change the graph in order to reach a goal that is to fill up a volume. And we call this graph-based reinforcement learning. And we have seen that if we also combine it with search during test time, it really outperforms any other method. And it can scale up to new, for example, number of objects in the scene. But it is a very difficult problem because it needs for the robot to explore, to try many different actions. And for that, we figured that the best way to actually help the exploration is to take ideas from the classical solver, try to consider how we could do a resource assignment of these building blocks without considering the robot in the loop, without considering whether the structure is really stable or not, and then use this set of solution as the action space, as the exploration space where the robot can really try out some combinations. So we used a classical model-based global optimization approach to get this data, and then we used our graph-based reinforcement learning approach to basically change the connectivity of the blocks with respect to the robot to make an assembly. And eventually, to execute, we just deployed classical grasp and motion planning to execute these assembly tasks. And here you can see how using just the heuristic model-based approach with some rule-based planning method fails because it doesn't take into account the physical constraints of the world and the fact that if you place two objects in a specific way, you may end up in collisions, while here our reinforcement learning approach combined again with search during test time can outperform and can eventually be transferred easily into the real world because you are doing decision-making on, let's say, higher level of abstraction, where it is just the object sequencing, and the robot can execute with different combination of these Tetris blocks, this kind of assembly task, only reasoning on the graphs, on basically the representation of the objects and the robot in the scene. But taking advantage of the graph-based structure of the world is very, very powerful, even if you want to append semantic information on these graphs. For example, what we would like to have is our robot here to give it a command to say, reorganize, for example, the toys in the cupboard. The toys are here, and there is some sort of graph structure, and we would need the robot to understand what are the interrelationships given this scene graph, as we call it, and to be able to reason on how it should sequence these actions. And now with large language models, it became evident that we can have some good representation of common sense knowledge there. However, these models are not grounded into the physical world. So what we try to do is to construct a geometrically coherent natural language context that basically takes the information from the scene graph and creates a context that represents the scene. And then we use this context together with the natural language commands in order to fine-tune a large language model, basically not so large given the current standards, but GPT-2 models in order to generate planning sub-steps. So what do you need to do in order to, on a high level, in order to solve this task? And then on the low level, in order to achieve these sub-tasks, you use classical planners that they also have guarantees of completeness, and if something goes wrong, you can feed back and requery new steps from your neural model. Therefore, how does it look like on a very high level? This is just a simple room. This is the scene graph that represents objects, and the connection just represent relations. In our case, this represents some geometric relation that we translated into natural language. This is the bathroom environment. So it says that closer, below, and left of the sink, near, below, back of the soap bar, you try to find where is the soap bar, and you try to basically create natural language context of all the possible relations that you have in the scene graph. And you create this context, and together with your command, you train what we call the RobLM, so the robotic language model that can output this high-level plan that I was telling you. So the task here is put the soap in the drawer. It starts with go to location of the countertop, pick up the soap, go to location drawer, put object, soap into drawer. And then its sub-goal here gets executed by a classical planner. And by reducing the search space for the classical planner, you make basically the problem way more efficient and eventually scalable. And then if something fails, you can go back and query again your neural model, or even in the future train it with reinforcement learning via trial and error in order to improve on the task and always ensure that it is grounded on the object that you have in the scene. If you ask me, we tried, yes, also with GPT-3, we tried with also now with newer models. Sometimes they are good, sometimes they are not so good. They are very sensitive into prompting, so I think having a specific model that generalizes to this specific task of house rearrangement, it's, in my opinion, way more important than having a multi-modal, multitask large language model that may or may not work well on the specific task. And eventually, we, of course, want a robot like this robot, the Tiago robot that we have in our lab, to be able to execute this plan. It's not only about high-level reasoning, but it is also about physical interaction. And how can we coordinate this robot to understand what is its own reach? How should I place my body with respect to the environment in order to understand, can I grasp now? Should I move like this? Should I move like that? How should I position my body in order to open, for example, a drawer? These are problems that we have not solved yet. So in a work that we presented last year in IROS, a robotic conference, and we also got a Best Paper award, we proposed a hybrid reinforcement learning approach that reasons both on continuous and discrete variables of decision making. Where should I place myself? Should I now do manipulation, yes or no? And by training this method with a classical inspired, let's say, robotics prior that takes into account the structure of the robot itself, we were able to, as I will show you in a while, perform autonomous mobile manipulation in sequence. So what did we did here? Classical methods in mobile manipulation, they would take, this is called the workspace of the robot. So you discretize the reachability area of the robot, and this is a discretization of 3D positions and 3D possible orientations, and you try to solve how many times you can find a solution. This is an optimization approach, and you try to find how many times can I find a solution in the space given a specific pose. Now, if we take this workspace, and with a specific technique, you can actually invert it and cut it on the level of the floor, and then you cut then you get what we call the inverse reachability map. That is basically a discretization of the space in positions and orientations of the base, where if you place the robot in this, let's say, bluer area, there is a chance of actually finding a solution of reaching this specific target. But this is very, very expensive. You have to assume that you have queried all possible 60 targets and that you have them somewhere stored, which is not very, very efficient. So we considered, why don't we use this data together with the actual success of reaching a target, or for example, grasping an object, and train a reinforcement learning agent on this data to learn a continuous function approximation over this space. And you can see how this looks compared to this more engineered method. And eventually, we can use this initial map as a prior, and by doing boosting, by basically subtracting your problem into learning smaller functions, you can transfer this knowledge into learning more and more complex tasks. So initially, we started by just reaching random 60 targets in simulation. Then we transferred this into a more complex task where you have also obstacles, where you do different sorts of arrangements. Then you have to also grasp and find clearance in order to grasp objects. And we can transfer this into the real world with the robot being able to adapt to the whatever arrangement we do in the environment, because the robot, again, has knowledge of the poses of the objects into the scene connected to the robot. And you can eventually do sequential rearrangement. So the robot can place itself and reason on, OK, now I have to move this object from this table to the other, and I need to take the minimum amount of steps in order to execute this task. And believe me when I tell you that in order to drive the robot to do this, with a joystick, it's very, very difficult. And the agent just found the best way to find a solution on the manipulation while placing itself in a position that maybe doesn't look really natural to us, but it basically solves the task. And of course, the perception part of the scene is something very, very important for the robot to be able to reason, especially when there is big clutter in the scene. So we took advantages on neural geometric representations and surface rendering from computer vision research. And we used representations that they render the scenes as point clouds. These are 3D points in the environment that they show you if something is occupied or not. That this you take directly from a camera. But as you can see, it's usually some sort of weird view of the environment. You don't really know what are the geometries of the object. So we trained a network that can actually can reconstruct the scene and the objects in the scene. And this is how, for example, the view looks like. It tries to complete the scene and render the exact geometry of the environment. And then by reimagining grasping as rendering itself, so by creating virtual cameras on the hand of the robot, we can learn features that enforce the complementarity between the end effector of the robot, the hand of the robot, and the geometric surface of the object. So then you can extract way more informative information about the interaction between the robotic hand and an object. And eventually, you can also learn to reconstruct better the scenes, given that you have more local rendering information. And so how this looks like, you get a view, a single view of the environment. You reconstruct the scene, and then you do a sampling of possible grasps, and then the network that we created can evaluate if this is a feasible grasp or not. And therefore, you can do any viewpoint grasping. Here you can see the robot is doing a decluttering task. And given that the robot has basically now learned a mental model of shapes of objects in the environment and geometries, it can eventually move around and get different random views and go back and, for example, drop the object in the basket as we want it to sequentially. And what additional thing that these methods can give you, once you get, let's say, a perception module, you can extract uncertainty about how basically certain you are about the representation of the scene or the grasps that you have found. And you can use information theoretic methods in order to drive the exploration of the robot on how it should move in order to get a better view and then grasp the objects in the environment. Neural representations are also very important because it allows us to represent the geometry when the robot has to interact, for example, with humans. And especially one big issue in robotics is how do we get continuous constraints, constraint functions in order to understand whether a robot has collision or not. And this usually, with classical approaches, requires a lot of engineering and methods that may not be really scalable when it comes to rearranging an environment and be able to do dynamic manipulation when you have like moving obstacles and so on. So what we did in another work is to take advantage of these neural geometric approaches in order to learn what we call sign distance fields, a function that represents whether or not a point belongs to a surface of the robot, of any object in the scene. And then you can get very, very fast distance measurements because you can basically query these models in batch. And you can basically now use this information to learn surfaces of articulated objects, like, for example, humans, and this is the comparison of our reconstruction of the surface compared to some other methods in the literature. And then you can use this and query it in batch and change, for example, the distance of interaction, and basically create some sort of safe surface area around the human when you want to interact with them. And of course, here we didn't arrive to the interaction because it's very, very complicated to have good physical interaction with humans, but we are looking into safe reinforcement learning about how we can exploit the geometry and the topology of different constraints, also constraints that come from this kind of neural models, in order to transform the actions that the robot can do to always enforce them to not violate the constraints. And what does this mean? This means to map them into a space where the actions will be tangent on a constrained surface, on a constrained manifold, as we say. And then we can guarantee that locally we will never violate the constraint. And this allows us to eventually learn how to interact with humans, that the humans are randomly moving around in the scene. Here, the robot has to deliver a glass of water, let's say. And the human is instructed to look at the phone, not paying attention at the robot, and like reaching out to take this orange from the table. And the robot has learned to, given these neural representations that give you the geometry of the scene, the robot has learned to always try to basically deliver you the glass while avoiding all collisions with the human that randomly changes its pose in the scene, and of course with the robot itself, with its own body, and also with the static objects like the table in the scene, without ever overturning also the glass, which was an additional constraint that we had in our learning algorithm. So yeah, this brings me to a conclusion. I would like to shout out to all the students and collaborators that work with us on these very challenging problems. And obviously, there is still a lot of work to be done and to bring robots into the real world. So my takeaway message from this talk for you is that I believe that we should consider the fact that we are standing on shoulders of giants. There have been a lot of work before us in planning and classical control that can be combined with machine learning methods when we bring, for example, the appropriate representations in order to make these approaches basically function in these different spaces, representation spaces. I believe that we need to focus on using structure of the problem because this is the way to scale robotic behaviors, and also the structure and the geometry of the environment where the robots operate in order to ensure smooth and safe interactions. And I believe that learning for mobile manipulation, learning for such complex systems that combine different embodiments, different sensors, is a very challenging topic and is the way to achieve embodied intelligence. So thank you very much for your attention, and I'm open for questions.
Thanks a lot. We open again up the stage for questions. Just raise your hand and we will come with the microphone.
Thank you so much for the entertaining talk. It was really fascinating. I have one question regarding the reachable workspace that you mentioned. So have you also mapped a similar case for the dexterous workspace of a mobile manipulator?
Yeah, actually, this is not just the reachability space. It takes into account the manipulability index, which means whether or not if I reach this pose would allow me to really manipulate an object. So yeah, very good question.
Yeah. Okay. Thank you.
Is there another question?
Are there more questions? It's difficult to see with the light, so just wave if we don't see you. So then maybe I can ask a question. So you showed now all these nice videos where it worked. How does it look like when it fails?
So there are different reasons of failure. One reason is the hardware itself. So after operating the robot, after some time, the motors of the robot start to overheat. So even if things look okay in the simulator, the execution doesn't match what is happening in the real world. So this is something that we also need to take into account and model. And the same comes also like with the perception part. Like when you may have like sensor failures, you may miss, for example, frames, which again, then you have a mismatch of what is happening in the reality. So in my next steps, how I would like to counteract it, it's definitely by quantifying uncertainty and trying to have some sort of like safe policies. And also we are looking into making our methods robust and adaptive. So being robust to certain events like sensor failure, but also being fast adaptive to a new, let's say, behavior that doesn't break the robot or the environment. Yeah, thank you very much.
Then let's thank our speaker again.